this video, we're going to continue our survey of basic functions, and we're going to be looking at polynomial functions in this video. So, polynomial functions have sort of two good forms. One is the standard form, which is written out this way, or expanded form, where it's some constant a sub n times x to the n plus a sub n minus 1 times x to the n minus 1. If this first a is not 0, then this is called the leading term, and that a sub n is called the leading coefficient. N is called the degree of that polynomial. This last term, the constant term here, is going to be the y-coordinate of the y-intercept, because you see if you plug in x is 0, all these go away. And then we can also see it factored as that same leading coefficient, an, times x minus root 1 to some power, m1, x minus root 2 times some power to some power, and so forth. And it'll always factor all the way this way down if we allow complex numbers for these r's. It'll factor, if we start with real number coefficients, then it'll factor down this way into quadratic and linear terms if we only allow real coefficients. Now these r's that correspond to real numbers, that are real numbers, they correspond to x-intercepts. So r1 comma 0 and r2 comma 0 are x-intercepts if these r1 and r2 are real numbers. These powers here are called the multiplicities of those roots, and if you sum, of course, all the multiplicities, you're going to get this power n up here. So the first thing we want to know is are polynomial functions continuous? And you probably already know that they are. But if you look at the proof, it's pretty straightforward. Each one of these terms here is a power function, and we've already proved that power functions are continuous, and we know that the sum of two continuous functions is continuous, and so there's the whole proof that that is continuous. And it's not only continuous where it's defined everywhere, so polynomial functions are one connected piece all the way across. Now let's look at some characteristics that the graphs would have. All polynomial functions have the entire set of real numbers as their domain, so they're defined for all real numbers. They're continuous, one connected piece. And in our next unit, we'll talk about what's meant by differentiable, but that's going to be means they're one connected smooth piece. They do not have asymptotes, vertical or horizontal. They do not have any sharp corners. They don't have any holes in the graph. So they're kind of well behaved. Now what they can have is some local extrema and inflection points, as well as some x and one y-intercept. They always have exactly one y-intercept, and they might have several x-intercepts. They have exactly one y-intercept. Its y-coordinate, as I said, is the same as this constant term right up here. And they can have several x-intercepts. The number of x-intercepts goes up with the degree of the polynomial. So the number of x-intercepts can go up to the degree of the polynomial. So if this power n, highest power, is 5, let's say, then there could be 5 of these factors, all of the first power, and so each one of those could be 5 different roots. So it could have up to 5 places it crosses the x-axis. So the number of x-intercepts can go up to the degree of the polynomial. The x-intercepts correspond to real roots, which correspond to linear factors. The multiplicities of the real roots affect the shape of the graph near these x-intercepts, and I'll show you an example of that here in a minute. For simple roots, multiplicity 1 roots, the graph passes directly through, somewhat like a line if you zoomed in close. Even multiplicity roots, then they will touch the axis and turn around, so that'll be an x-intercept, but it'll also be a local extremum, a local maximum, or local minimum. And odd multiplicity roots, if the multiplicity is greater than 1, like multiplicity 3 or 5 or 7, for example, then the graph flattens out as it passes through the x-axis, but it does go on to the other side, and that point's both an x-intercept and an inflection point, and furthermore it has a horizontal tangent line at that point. Some of this we'll explain a little bit more why this works when we get to studying derivatives. They can have several extrema. The local extrema, that's maximum and minimum, those are singular. Maxima and minima is plural. We don't care whether it's maximum or minimum, we call it an extremum. So they can have local extrema, and they could have several, up to one less than the degree of the polynomial. So if it's a degree 5 polynomial, they could have up to 4 extrema. And they're evenly dividing into maximum minima. If there are 4 of them, there'll be 2 mins, 2 maxes. If there are 3, then there'll be either 2 mins and 1 max, or 1 max and 1 min. If it's an even degree polynomial, it has a global extremum, and so the arrows on the end point the same way. So if the leading coefficient is positive, it'll be pointing up on both ends. The limit as x goes to infinity and the limit as x goes to minus infinity are both infinite, positive infinity. And so somewhere in the middle, it'll have a global minimum. On the other hand, if the leading coefficient is negative, then the arrows point down on both ends. The limit as x goes to infinity or minus infinity is negative infinity, which means, of course, it doesn't have a limit. It goes down forever. And somewhere in between, there'll be a global maximum. On the odd degree polynomial functions, they do not have a global extremum. The range is all real numbers there. And of course, if you have an even degree polynomial, if it's a positive leading coefficient, the range will be from that global minimum up to infinity. And if it's a leading coefficient negative, it'll be from negative infinity to the maximum. But odd degrees, the range is all reals. The number of inflection points can go up to 2 less than the degree of the polynomial. So again, if we go back to degree 5 polynomial, it could have at most 3 inflection points. Sometimes it has less than these things, but that would be the most. The end behavior of the polynomial function is the same as the end behavior of a power function. That's that first power, that leading term power function. And so, again, don't look at what's in the middle here, but look at what's on the far ends, the far left and right. If it's an even power with a positive leading coefficient, it's up on both ends, like this. If it's odd power and leading coefficient, the leading coefficient tells you what happens on the right side. Positive leading coefficient says it's increasing on the far right, pointing up. With the odd power, one's going to be pointing up, one's going to be pointing down on the arrows. Negative is just upside down, so negative leading coefficients can be pointing down on the right. Even power for the highest power, they'll both be down on the right. And then opposite here for the odds. So for example, here's one. Here it is in factored form, 1/5000th times x plus 8 times x plus 2 cubed times x minus 7. So notice when x is negative 8, when x is negative 2, and when x is 7, we get y is 0. So those are what we call our roots, or their x-coordinates of the x-intercepts. And notice the powers here are the multiplicities. Look at the shapes of the graphs there. When it goes through negative 8, 0, it kind of goes through kind of like a straight line. Not exactly straight, but kind of straight through there. This multiplicity 3 root at negative 2 right here, it comes up, flattens out, and then turns back around. Looks a little bit like, y equals x cubed does at the origin. Okay, and then this one over here is a little bit more like x squared looks like it at the origin. It touches and turns around. That's a multiplicity 2 root. Multiplicity 4, 6 root would look kind of similar to this. Now it might be down here, upside down, and this one could be opposite, coming down and then down this way. But an odd multiplicity root like 3 or 5 or 7 multiplicity root would look very similar to this. Notice this does have its even degree. I can tell because, among other things, both the arrows are pointing the same way as on the ends. Also, I add up these powers here. 3 plus 2 is 5, plus 1 more is 6. So the first term, if you multiply this all out, will be 1/5000th x to the 6th, and it's got plus a bunch of other terms. But the end behavior should look like 1/5000th x to the 6th. So if I just graph this function with this, you'd see that the ends look pretty close to the same, even though the middle wouldn't look anything at all the same. It does have some extrema. There's a global minimum here, which is a local minimum as well, another minimum over here, and a maximum here. So with degree 6, it could go up to 1 less, could go up to 5 extrema, but in this case it only has 3. A degree 6 could have up to 4 inflection points, and let's see how many this one has. It has 1 in here. The inflection point is when it changes from concave up to down or down to up. So it's concave up here, like a right side up bowl. Then this is like part of an upside down bowl here, so it's concave down here. Somewhere in here, it's hard to see exactly where it is, but maybe about here it changes. Then one of them is actually right there at the root. That's another inflection point. Now it switches to concave up. There's another inflection point in here somewhere where it switches to down. Another one here, it goes back up. So the inflection points are 1, 2, 3, 4, which is the most you could get for a degree 6 polynomial. Okay, so that gives you a very, very quick overview of polynomial functions. Again, as I've mentioned earlier, you should probably look at my algebra videos for a much more in-depth investigation into polynomial functions, but that gives you a nice quick overview, and notice they are a good example of a continuous function.